Well, another variant of osmotic pressure model is known as the Kedem-Kechelski model. This is a variation of osmotic pressure model and the difference here is we expressed the osmotic the solvent flux as Lp times delta P minus sigma delta pi. This sigma is a new thing that is incorporated here, and this is known as reflection coefficient. This reflection coefficient indicates how the amount of some amount of solute is always reflecting back and some amount is going through the membrane system. If it is that means fraction of solute reflected back to the feed solution or feed system, and rest are permeating through the membrane or passing through the porous membrane. So, therefore, this sigma is always a fraction. Sigma is equal to 1 indicates that purely retentive membrane. Sigma less than 1, that means solutes, some solutes are permeating through the membrane. So, this reflection coefficient is again an unknown parameter, and it has to be estimated from the method, the optimization method I just mentioned earlier. Now, if you look into the expression, if you look into the linear relationship of osmotic pressure and concentration, linear osmotic pressure and concentration relationship, the expression of J becomes Lp delta P minus A sigma Cm minus Cp, and one can combine this equation with the film theory equation. Cm is equal to Cp plus C naught minus Cp exponential j by k, and one can combine these two equation and replaced Cm in terms of Cp, and this becomes J Lp times del P minus A sigma Cm minus Cp. So, it will be C naught minus Cp exponential j by k. Okay. Now, so and the other equation you must be you are having two equation two unknowns and one equation J and Cp, and the other equation will be coming from the solution diffusion model. Solution diffusion model is basically J is equal to B Cm minus Cp divided by Cp, and or the definition of real retention Rr is equal to 1 minus Cp by Cm. So, in your system there are three unknowns J, Cm and Cp. You must be having three equations to solve these three unknown. First one is the Darcy's law, second one is the film theory, third one will be the either solution diffusion model or definition of real retention. Again, three equations and three unknown have to be solved by trial and error method solution. And J and Cp can be obtained. Now, if you use solution diffusion model, you will be having two parameters to be estimated from the experimental data. One is solute permeability through the membrane, another is the reflection coefficient. If you use the definition of real retention, you will be having only one parameter, that is the reflection coefficient, and real retention can be estimated from a separate set of experiment. So, this is a variation of osmotic pressure model in terms of reflection coefficient. This is known as the Kedam-Kechalski equation. Next model we will be looking at, it will be more realistic. This is known as the modified solution diffusion model, or solution diffusion imperfection model. In this model, we will be assuming that some amount of the solute will be transported through the membrane not only by diffusion, but also by convection, because of presence of higher pore sized membrane in the membrane matrix. So, JCP, the modified diffusion model becomes J times Cp is equal to B times Cm minus Cp plus 1 minus sigma J times C average. This is the solute flux through the membrane, B is the solute permeability through the membrane. Up to here, up to the first term on the right hand side, it is a solution diffusion model, it is identical to the solution diffusion model, and this is 1 minus sigma J times C average is basically due to convection. Due to convection, this is due to diffusion. Sigma is the reflection coefficient. Sigma is the amount of fraction of the solute that has been reflected or retained by the membrane. So, 1 minus sigma will be the fraction of the solute that will be permeating through the membrane, multiplied by C average. What is this C average? Because you are having a gradient of through the membrane, this is the membrane. At the membrane surface you are having Cm, in the permeate side you will be having Cp, there will be again some kind of gradient existing. Now, this concentration will be which concentration? So, that is a problem, whether Cm or Cp or and any concentration in between is not known to you. So, it is taken as log mean average temperature, average concentration. It is like the definition of LMTD. Okay. Log mean average temperature, it is exactly like that. C average is taken as Cm minus Cp divided by ln Cm divided by Cp. This is known as the log mean average concentration of the solute in the membrane system, within the membrane. Now, so this will be one equation. The second equation will be the Darcy's law, solvent flux through the membrane, J is equal to Lp times delta P minus sigma delta pi, and the third equation will be the film theory equation. That is J is equal to K ln Cm minus Cp divided by C naught minus Cp. Three unknowns J, Cm and Cp, three equations and three unknown. It satisfies its degree of freedom and can be solved. So, one can get a system performance J and Cp as well as Cm. Now, again in this case the parameters, what are the parameters of the model? There are two parameters B and sigma. Okay. These two parameters will be estimated by the by comparing the calculated values of J and Cp with the experimental data and minimizing the sum of squares through the optimization technique. Okay. Now, depending on the situation, one can have actually these three, all these methods are applicable for. Now, let us look into the applicability of these equations. Applicable to system, which system? Reverse osmosis, nanofiltration, ultrafiltration. The microfiltration is entirely different, it is basically cake governing system, and these ultrafiltration are lower molecular cutoff ultrafiltration. Lower molecular weight cutoff ultrafiltration. For higher molecular weight cutoff, you will be having the cake governing mechanism. Now, for RO, you will be having the RR method or solution diffusion model is good enough. Either RR or solution diffusion model is good enough, because reverse osmosis contains very small pore size. So, it is fair, it is good enough to assume that the solutes will be transported by diffusion through it. In nanofiltration, there are some more, there are pores which are basically in nanofiltration are open RO membrane, the pore size is slightly larger. So, either RR method or solution diffusion, modified solution diffusion model will be applicable. Why RR is applicable suitably in all these cases? Because it is basically a parameter which will be estimating from a separate set of experiment. So, it will be dumping all the effects of solute transport to the membrane. Okay. In the case of lower molecular cutoff ultrafiltration, either RR method and modified solution diffusion model will be good enough. Okay. In fact, these will be more appropriate for ultrafiltration, because ultrafiltration pore sizes are much larger, where the convection plays a dominant role as far as the transport of the solute through the membrane is concerned. Now, we identify the various, as we have earlier said, that during the modeling we have to have the transport outside the membrane and transport within the membrane. Now, let us identify the equations which correspond to the transport outside the membrane. Outside the membrane means within the flow channel. And transport inside the membrane. Transport outside the membrane is basically the film theory equation. If you remember the derivation of film theory, we solved the concentration boundary layer outside the membrane, and we arrive at J is equal to K ln Cm minus Cp divided by C naught minus Cp. K is the mass transfer coefficient or inverse of the resistance of mass transfer boundary layer or concentration boundary layer, and transport inside the membrane given by Darcy's law for solvent flux. J is equal to Lp del p minus del pi or sigma del pi, the variant of that, is one, and second is the solute flux. Solute flux is solution diffusion equation. J Cp is equal to B times Cm minus Cp, that is the solution diffusion equation number 1, or it can be a modified solution diffusion equation, or number 3 is simply the definition of real retention. So, in case of solute flux, either one can use definition of real retention, or one can use solution diffusion equation, or one can use a modified solution diffusion equation based on the system and accuracy of calculation you require for your system. And transport through the membrane can be defined by the Darcy's transport of solvent through the membrane can be defined by quantified by the solvent flux by Darcy's law, or a modified Darcy's law by including the reflection coefficient. And transport law outside the membrane is solved by solving the concentration boundary layer equation in order to obtain the film theory equation. Okay. Now, all these whatever we have talked or discussed till now, it is the first generation model or the simplest kind of model. So, we have to go for the next generation model for getting better accuracy. In order to go for the next generation model, we have to identify what are the shortcomings of this present model. Okay. Now, let us write down the limitation of film theory or shortcoming of the film theory. If you remember or if you can notice that all the first generation models that we have discussed till now, the one equation remains intact, that is the film theory model, film theory equation. Film theory is obtained by looking into the concentration boundary layer that is existing outside the membrane, assuming that the thickness of concentration boundary layer or mass transfer boundary layer is constant. Okay. So, the first limitation is constant assumption of constant thickness. Of concentration boundary layer. In fact, we have discussed earlier the entrance length required for a concentration boundary layer will be much larger compared to the entrance length required for a hydrodynamic boundary layer, because of high Schmidt number present of this system. High Schmidt number will be reflected because these solutes will be having very low diffusivity. So, therefore, if we use the film theory, a substantial portion of the channel where the boundary layer is developing is not encountered or not taken care of. Therefore, the permeate flux that you will be obtaining is using the film theory equation will be under predicting. So, that is one limitation, the thickness of concentration boundary layer is assumed to be constant. Actually, the concentration boundary layer is developing. Right. Second assumption, if you look into the expression of Sherwood number, the mass transfer coefficient, mass transfer coefficients were estimated from the expressions of Sherwood number, and these Sherwood number relations are all obtained from heat and mass transfer analogy. Okay? Obtained from the Sherwood number relations or correlations for the turbulent flow, and these are obtained from heat mass transfer analogy. And if you remember the heat and mass transfer analogy, the cases for heat transfer are for the porous conduit, non-porous conduit, impervious conduit. If the conduit is impervious, those cases are solved or obtained by the heat transfer experiments. They develop the expressions for the Nusselt numbers using heat mass transfer analogy. These Nusselt number expressions are transformed into the Sherwood number relations. They are valid for impervious conduits. On the other hand, our cases, the conduits are porous. So, therefore, the Sherwood number relationship that we are using for estimating the mass transfer coefficient are not correct. They should be corrected for the for taking into account the porosity of the wall or the suction parameters. The some amount of fluid will be sucked up, and so there will be porosity or suction is not taken care of by the film theory equation. This is very important in case where the the wall is more permeable. For example, microfiltration membrane, we will be having more porous wall, more porous membrane, that means pore sizes are very large. In case of reverse osmosis, the pore size effect will be very small, because the pore size itself is very small, 2 to 10 angstrom. So, this inaccuracy becomes very predominant in case of ultrafiltration and microfiltration. They are not that important for in case of reverse osmosis and nanofiltration. These two are major assumption or limitation of the film theory in its standard form, whatever we are taking. The third limitation is very true, that the physical properties are taken as constant. Now, let us look into the what are the physical properties that are involved in such cases. One is mu, there is the viscosity, density rho, and diffusivity d. These three transport coefficients are quite predominant in this case of mass transfer. Now, we know all these three properties, thermophysical, kinetic properties, are functions of concentration. In fact, out of these three, viscosity is the strongest function of concentration. Rho and d are weaker functions of concentration. Between these two, density is the weakest function of concentration. If you remember, in the polarization layer, the variation of concentration is from C0 to Cm. In some cases, Cm can be as high as 10 times C0. So, therefore, there exists a stiff concentration gradient within the mass transfer boundary layer just outside the membrane. So, whenever there is such a tremendous change in concentration, all these physical properties are supposed to be affected, and they will be reflecting into the definition of the mass transfer coefficient, and mass transfer coefficient will be altered. Now, all these changes or limitations are not reflected in the film theory. So, what we will do in the next analysis? In the next analysis, we will try to overcome the first two limitations that we have mentioned in this list of limitations, that is the constant thickness of mass transfer boundary layer. We will do an analysis where we will be considering the developing mass transfer boundary layer with the porous wall. The third one, the variation of physical properties, it is very quite difficult to capture these features fundamentally. There are few papers that I will be telling you in the references that are available in the literature in the next class, some of the references done by my group, and mostly these changes are incorporated in the form of correction factors included in the mass transfer coefficient, like Cedar-Tate correction factor in the Nusselt number relationship. Okay. Let us look into the how we can analyze a developing mass transfer boundary layer, so that the first two limitations of the film theory can be overcome. Mass transfer boundary layer and concentration boundary layer, they are identical. So, I am drawing a rectangular channel. Okay. The flow is occurring here, and the coordinate system y starts from the bottom, and you will be having x axis. So, 0 to L, x is equal to 0 to x is equal to L, and this is the membrane. And we can assume a fully developed velocity profile. Let us consider a laminar flow. we can extend this analysis to a turbulent flow as well, that I will talk later on. We can assume a fully developed velocity profile, that means a parabolic profile is existing, simply because we have seen that hydrodynamic boundary layer, the entrance length required is LE by DE time is equal to 0.05 times Reynolds number, and for the laminar flow maximum Reynolds number will be around 2200, and the channel dimension, that whatever we are talking about, it will be in the order of 1 millimeter. The equivalent diameter will be roughly in the order of 1 millimeter. So, with these dimensions, the entrance length for the hydrodynamic boundary layer becomes few centimeters, 4 centimeter, 5 centimeter, 6 centimeter, like that, whereas the channel length we are talking about in terms of meters, 100 centimeter. Okay. So, we can neglect the initial portion of the developing hydrodynamic boundary layer and consider that 99% of the channel, the hydrodynamic boundary layer is fully developed. On the other hand, mass transfer boundary layer is still growing because of the existence of very high Schmidt number. Okay. So, mass transfer boundary layer will be growing something like this. Now, if we see that initially at the channel entrance, the mass transfer boundary layer thickness will be extremely small. So, it will offer very less resistance against the solvent flux. So, you can expect a very high solvent flux in the beginning, and slowly it is growing. So, it is offering more resistance against the solvent flux. So, it will be decreasing slowly. Okay. Now, when this becomes almost constant, this becomes the resistance is also constant, and we will be getting a constant permeate flux. So, therefore, the productivity of the permeate flux is also obeying a kind of profile. Now, in the film theory, whatever we have done earlier, we are assuming we are basically working on the later half portion of the mass transfer boundary layer, where the thickness becomes constant. Here delta is growing, delta is the concentration boundary layer thickness, that is a function of x, but here it is independent of x, whatever the value of x you take, it becomes constant. So, in case of film theory, we are not accounting this amount of flux, which are basically higher flux, therefore, it gives an under prediction. On the other hand, in this case, we will be accounting these initial values of the flux as well, in addition to the later on values. Okay. So, let us write down the assumptions involved in this analysis. One is steady state flow, second is laminar flow, laminar fully developed flow, fully developed in the sense of hydrodynamic boundary layer, but developing in the sense of, so fully developed means fully developed velocity profile or hydrodynamic boundary layer, and third is no adsorption of solute on membrane surface. Okay. So, the whole phenomena should not be coupled with the adsorption phenomena, complications like adsorption. So, adsorption is not there. Okay. That means, LP, the permeability of the membrane remains intact. Now, with this we are going to do an analysis of developing mass transfer boundary layer over the membrane surface. Now, what you have to do? First, you write down the transport equation outside the membrane, that becomes very important now. We will write down the transport equation outside the membrane, we will write down the transport equation inside the membrane, and among the transport equation we will be using the Darcy's law for solvent flux, for solvent transport, and we will be using the real retention for solute transport. This can be replaced by any of the modified versions like solution diffusion model, modified solution diffusion model, or things like that. Okay. Just for the sake of simplicity, we will take the real RR, the definition of RR for the solute transport. Now, let us write down the transport equation outside the membrane. Outside membrane, but within concentration boundary layer, within mass transfer boundary layer, within concentration boundary layer or mass transfer boundary layer, because outside the concentration boundary layer or mass transfer boundary layer, everywhere concentration is same. The concentration is C naught everywhere. So, there is no point in writing any balance equation there. So, whatever the equation we are writing outside the membrane, that is within the concentration boundary layer or mass transfer boundary layer. Now, in this context, I will just take a diversion, and I like to emphasize the importance of any boundary layer analysis. For any boundary layer analysis, heat transfer, mass transfer boundary layer, thermal boundary layer or hydrodynamic boundary layer, the thickness of these boundary layers are extremely small. They will be typically in the order of microns, 10 to the power minus 6 meter. On the other hand, the actual channel dimensions or the flow dimensions will be in terms of millimeter or centimeters. But these boundary layers are very thin, but within these boundary layers all the transfer processes will occur. Momentum transfer, heat transfer or mass transfer will occur within that thin boundary layer. That is why these boundary layer analysis are very important. Although the boundary layer thickness is extremely small, you cannot neglect the boundary layer analysis. Okay. So, let us write down the transport equation outside the membrane within the concentration boundary layer. We write down the solute balance equation. The solute balance equation will be simply U del C del x plus V del C del y is equal to d del square C del y square plus d del square C del x square. Right, the z dimension is too long. So, therefore, we write a two dimensional equation. It is a steady state. So, therefore, there is no del C del d term. X is along the membrane length, y is in the vertical direction, in the transverse direction. So, this is the convective term in the x direction, convection in x direction, convection in y direction, diffusion in x direction, diffusion in y direction. Typically, the axial velocity u for the laminar flow will be ranging from 0.1 to 0.4 meter per second, 0.1 to 0.4 meter per second. On the other hand, the diffusivity will be in the order of 10 to the power minus 10 to 10 to the power minus 11 meter square per second. So, therefore, the convective term in the x direction will be much larger in magnitude compared to the diffusive term in the x direction. So, we can safely neglect the diffusive term in the x direction. So, these three quantities will constitute the solute mass balance within the mass transfer boundary layer. Now, in order to get an exact estimate, you should insert the profile of u, the velocity profile u and v in the above equation. If you do that, what is the velocity profile in the x direction? We consider it is a fully developed velocity profile as far as the hydrodynamics is concerned. Therefore, the parabolic velocity profile will exist. For a rectangular channel, this will be a function of y only, and it is 3 by 2 u naught into 1 minus y minus h divided by h square of that. This is the velocity, the parabolic velocity profile in the rectangular channel. What is u naught? U naught is the cross sectional average velocity. This is a measurable quantity. How will you measure it? You put a rotameter in the flow path and measure the flow rate. You know the geometry, you divide it by the cross sectional area, the velocity that you will be getting, you will be getting the value of u naught. So, this is the velocity profile in the x direction, and if you remember that concentration boundary layer thickness delta will be of the order of 10 to the power minus 6 meter. On the other hand, the half channel height, this is half channel height, this will be in the order of millimeter, 10 to the power minus 3 meter. So, if you just look into the diagram, this is the velocity boundary layer and this is the concentration boundary layer. So, we do not require the full velocity profile to solve this equation, because this equation is valid within y is equal to 0 to y is equal to delta. We require only this portion of the velocity boundary layer. And what is this portion? This is almost linear, right? This is almost linear, and how can that be obtained? If you neglect y by h square and higher order terms, that means y by h square will be very less than 1. That means h itself will be 3 order of magnitude higher compared to y. So, therefore, y by h will be in the order of 10 to the minus 3, square will be 10 to the minus 6. So, you can neglect that. If you neglect that, you will be getting the linear profile of velocity. That means u is equal to 3 by 2 u naught 1 minus y square by h square plus 2 y h minus 1. Now, 1 will be cancelled out and y square by h square will be pretty small, that can be neglected. So, this becomes 3 u 0 y by h. So, you obtained a linear velocity profile that is valid within the concentration boundary layer. Okay. So, we finalize the velocity profile in the x direction. Let us look into the velocity profile in the y direction. We are going to have a permeate flux which will be a function of x at a particular location, and we are going to find out the y direction velocity within this mass transfer boundary layer. And since this mass transfer boundary layer, so there will be a velocity profile that will be existing, and at y equal to 0 its value will be minus j, right. The velocity will be this positive y. So, velocity here will be equal to minus j at y equal to 0, but we assume that since this thickness, this delta thickness will be in the order of 10 to the minus 6 meter, that will be extremely small. We assume the same velocity will prevail within that. Okay. So, v is equal to minus j within mass transfer boundary layer. This is a valid assumption because the thickness of mass transfer boundary layer will be extremely small. So, let us write down our governing equation. Our governing equation now becomes 3 u 0 y by h del c del x minus j del c del y is equal to d del square c del y square. Okay. This equation is known as the convection diffusion equation or advective equation. You require to have one boundary condition on x, you require to have two boundary conditions on y, because it is of order 2 with respect to y. Now, let us look into the boundary conditions so that we can solve them. At x is equal to 0, c is equal to c naught. At y equal to delta, you will be having c is equal to c naught. At y is equal to 0, at the steady state, all the fluxes towards the membrane will be equal to 0. That means, j times Cm minus Cp plus d del c del y will be equal to 0. This is known as a Robin mixed boundary condition. Okay. So, if you remember that this j times c, basically the convective flux towards the membrane, minus d del c del y will be a diffusive flux away from the membrane, j times Cp will be the convective flux away from the membrane. Since it is evaluated at y is equal to 0, I wrote c is equal to Cm. It is at y equal to 0 means at the boundary. Now, if you remember, this is the governing equation for the one dimensional problem, for the film theory equation. For the film theory equation, we solve this equation in order to get the governing equation. Now, for a two dimensional problem, so therefore, for a two dimensional problem, the governing equation of one dimensional problem has become a boundary condition for a two dimensional problem. Okay? Please identify that. Now, the point is y is equal to delta. Now, there is absolutely no problem regarding this boundary condition and this boundary condition. There is some problem regarding this boundary condition at y equal to delta, c is equal to c naught. At y is equal to delta, delta is the edge of the mass transfer boundary layer, but delta is not known to us. So, it is very difficult to solve the problem with unknown boundary condition. Your boundary condition has to be specified in order to solve a ordinary differential or partial differential equation. So, therefore, what is taken as that since this concentration boundary layer thickness will be 10 in the order of 10 to the power minus 6, most of the channel it does not affect, right, c becomes c naught. So, we assume that instead of this we can safely use the boundary condition that at y is equal to infinity, c is equal to c naught. In fact, the half channel height itself is although it is a real dimension is 1 millimeter, it is located at infinite distance away from the mass transfer boundary layer, because the ratio of h and delta will be in the order of 10 to the power 3. Okay. So, so that will be basically the 1000 times more it will be located 1000 times distant. So, therefore, it is taken as y is equal to infinity, c is equal to c naught. Now, let us what it does. This gives a tremendous handling to the solution of the problem. The solution technology becomes very simple. Solution method becomes absolutely simple by taking these assumptions. What is so great about it? The greatness of this boundary condition is that if we look into the governing equation, the partial differential equation, we can identify this is a parabolic partial differential equation. And this boundary condition simply indicate that one of the boundary residing at infinity. Now, whenever these two thumb rules are satisfied, that this governing equation can admit a similarity solution, or it is known as a combined parameter solution or similarity solution or a lumped parameter equation. What it does in a partial differential equations, you must be having at least two independent variables, right. The variables are x and y here. Now, in case of similarity solution, we define a combined variable of x and y, some form of functional form of x and y. Let us say eta is equal to y by x to the power half, eta is equal to y by x to the power 4 by 3, something, some combined parameter can be. So, whole governing equation and its boundary conditions can be expressed in terms of this combined parameter. So, that means you reduced number of parameters from 2 to 1. What does it imply? It implies you have reduced the partial differential equation into an ordinary differential equation, and the solution of ordinary differential equation is absolutely simple. So, it simplifies the whole solution. Now, the point is what will be the functional variation or what will be the similarity parameter. Similarity parameter is basically a combined parameter which will be a function of x and y, the independent parameter. Okay. What is this functional form? Whether it is y by x to the power half, or whether it is y by x to the power 1/3, or y by x to the power 4/3, or whatever it is. This parameter is known as the similarity parameter or combined variable, parameter, or a lumped parameter. Okay. Now, geometrically, before going into the actual calculation of evaluating the similarity parameter, I would like to tell you the geometric implication of this similarity parameter. If you plot C as a function of y, okay, for various x locations, the plots will be typically something like this. This is maybe at location x1, this is maybe at the location x2, this is maybe at the location x3. These are the various concentration profile across the channel. Now, so this goes from C is equal to 1 to whatever, okay. Because this is always greater than 1. Now, C at membrane surface divided by C naught. Anyway, now for combined parameter, if you plot or similarity parameter, if you plot this concentration profile as a function of y by delta, or that is how the similarity parameter is defined, okay, eta is equal to y by delta. Y by delta means the profiles, these profiles are known as the self similar profiles. So, if you divide by eta as y, define eta as y by delta, all these curves, all these individual curves will collapse on a single curve. Okay. So, you can represent all these number of curves on a single curve. Therefore, the existence of two independent variables x and y will be no longer there, it will be replaced by a combined parameter eta, and delta will be varying with a particular form of x, that will give you the variation, the relationship between y and x. So, instead of two parameters, you will be talking about one parameter, and PDE will be converted into ODE. So, that is how the similarity solution becomes very handy, and it reduces the PDE to ODE, and the solution of ODE are quite simple. Now, let us look into how to evaluate the similarity parameter. The evaluation of similarity parameter goes like this, and similarity parameter solution or similarity solution is quite rampant in case of boundary layer analysis, because in all the boundary layers, thermal boundary layer, concentration boundary layer, hydrodynamic boundary layer, the profiles, the concentration profile or temperature profile or velocity profile, all are self similar. If you remember, the governing equation was U del C del x plus V del C del y is equal to d del square C del y square. You insert the velocity profile, this becomes 3 u 0 y by h, h is the half height, del C del x minus j del C del y is equal to d del square C del y square. Okay. We evaluate whenever we are talking about a governing equation is valid throughout the whole control volume as well as on the boundaries, but the boundary conditions are valid only on the boundaries, but not within the control volume. So, this equation must be valid over the edge of the boundary layer. So, you evaluate this equation at the edge of boundary layer. At the edge of boundary layer, there are two conditions will be satisfied compulsorily, mandatory. What are the mandatory conditions? At the edge of boundary layer, at y is equal to delta, C is equal to C naught. At y is equal to delta, del C del y will be equal to 0. These two are mandatory for any boundary layer, whether it is a thermal boundary layer, hydrodynamic boundary layer or concentration boundary layer. In case of thermal boundary layer, at the edge of the boundary layer, T is equal to T infinity or T naught, and del T del y will be equal to 0. In case of velocity boundary layer, u is equal to u infinity and del u del y will be equal to 0 at y equal to delta. So, therefore, this term will not be there at the edge of the boundary layer. So, it becomes 3 u 0 y by h del C del x is equal to d del square C del y square. Okay. Now, we do an order of magnitude analysis, that means we take a small distance, let us say from 0 to x. Okay. This delta will be 0 to x and delta y will be 0 to delta. So, we do an order of magnitude of this equation. That will give you 3 u 0, y becomes delta minus 0 divided by h, and delta c divided by delta x becomes x minus 0 is roughly d del square C is nothing but delta c divided by delta y square is nothing but delta minus 0 square of that. If you ever do numerical differentiation, you can understand that delta square c is nothing but another difference in concentration. Okay? So, if you do the numerical differentiation, you can understand. So, this becomes 3 u 0 delta by h, this delta c will be cancelled, x is roughly d by delta square. So, this gives delta cube is equal to h d by 3 u 0 times x raised to x, and delta becomes h d 3 u 0 x raised to the power 1 upon 3. If you put the dimension of h d 3 u 0 and x, this becomes raised to the 1 upon 3 becomes unit of distance. Okay. So, what is the similarity parameter? Similarity parameter is eta equal to y by delta. So, this becomes y divided by h d by 3 u naught x raised to the power 1 upon 3. So, the variation of the combined parameter will be in the form of y divided by x to the power 1 upon 3. Okay. So, this is how the combined parameter is now evaluated, and now what we will do in the next class will be substituting this parameter in the governing equation and express our derivatives in terms of this combined parameter and reduce the PDE into an ODE and solve consequently. Okay. Thank you.